in any case, I'm at Mount Sinai, and my background is, I think Tom Perrine is here. There's a bunch of people here that I've worked with over the years. I've worked at the San Diego Supercomputer Center. And here I'll just start with this because it's on the slide. Before I came to Mount Sinai, I was working for the University of Tennessee at Oak Ridge National Lab, and so we deployed the third fastest machine in the world at the time. So that was pretty exciting, and I love the Kraken. Yeah, so I have some experience doing that, and I used to be a sysadmin. I don't know, maybe if once you're a sysadmin, you're always a sysadmin, I don't know. But yeah, so hopefully maybe I still qualify as long as people don't give me too many quizzes. But yeah, I worked at AccuWeather in Penn State and University of Wisconsin, New Mexico, and UCSD. So where I work now, you can see, so this is actually looking over Central Park from the Upper East Side. I don't know if you can see it. So so Mount Sinai, there's locations throughout the city, but where the main location is kind of in this 4-block radius around 98th and Madison and 5th Avenue, and kind of going like from 97th to 104th or something. So you can see there's this kind of big black building there, which the Wall Street Journal called it a Death Star, which is kind of true. If you've ever been in it, I mean, the windows are too high. Like if you sit down to work, you can't even see out the windows. It's poorly designed. But this new building, we actually worked in this building behind, but there's a new building there, this kind of tall, skinny building, which I'm already seeing in movies of New York City, which is kind of cool. When it was being constructed, but it's, so we have, the first 15 floors are for clinical work and research, and then they built this 30-floor apartment building on top of it, and so some of the funds from the apartment building helps to fund operation of the rest of it, so it's kind of interesting. But yeah, we have a school of medicine and a hospital. It's about a $7 billion a year organization in total with offices throughout the city. And yeah, you think 18,000 babies born each year, it's kind of like a small, little village, it's a lot. So the reason I came to Mount Sinai was they were looking for someone to help out with scientific computing. So you think, well, what kind of things do people do there? So it's things like molecular dynamic simulations, where people are trying to understand how proteins interact together so they can design a drug or to interrupt that interaction, right? To either treat disease or prevent disease and things like that. So I hope you can see how pretty this is, but it's a nice picture. Other examples of the kinds of things that scientists are doing are like, I'm sure you've heard about the precision therapy, personalized medicine, these kinds of things. So like Obama said he wants, or President Obama said this summer that we're gonna sequence 100,000 people, right? And so part of it is, you give two people have the same disease, you give them the same drug, it works for the one person, it doesn't work for the other, and you're thinking, why? Why is that? And I think a lot of the reasoning may be due to genetics. There's lots of stuff people don't know, but that's one of the things. So it's trying to come up with these different models and taking all the information about that and trying to turn it into knowledge and understand how to better to treat people. So I'll say, here's an example related to autism. So I think see if I get the numbers right, but I think we know about 100 such genes that are related to autism. We think there's about 500 that get expressed for this. And so there's still a lot that we don't know. So we have hundreds of thousands of genomes from people, from the mothers, sisters, brothers, uncles, whatever, and people are just trying to find the patterns to do it. So these are the kinds of things that people are using for computing. These are the kinds of things that people are using computing for at Mount Sinai, and also throughout at other medical schools throughout the country. Oh, and here's my favorite one, actually, is working on neurosurgery simulation. So for instance, you're thinking, like, there's flight simulators, all these things, so you think there must be neurosurgery simulators for people to practice before they operate on you, but there's not. And so when you start realizing, being in this place and finding out about all these sorts of things that, and ways that computing can help advance science and help treat disease, it's pretty exciting. So we've been actually working on a simulator that would have haptic feedback, right? And that, you're resecting a tumor, and, if you hit if you hit a vein, it actually kind of spurts the right way. And so trying to get all those equations and everything right for the, the finite element methods for the tissue deformation and all the blood flow models, which are, similar to turbulence models and other things that already exist in other parts of science. So in any case, this is super exciting. So actually, I'll tell you, it's kind of like the best thing that I've done since being at Sinai is I got to sit in on a brain surgery, which is like both the best thing and the worst thing that I've ever seen. I mean, the sounds and the smells, I mean, it's just really incredible. It's just really totally amazing and horrifying. So I don't know, it's very interesting. So I started at Mount Sinai in 2011. And it's for a lot of the reasons I said. I mean, it's interesting to learn about all these different areas of science and try to see how, what we can do to help. I mean, Sinai is actually special from the standpoint of there's the medical school and there's basic science researchers affiliated with it, but it's very tightly tied to the hospital. So you can actually, there's a very close partnership, so you can actually do things that will actually help with patient care. And I think a lot of other places I've worked, it seems like the hospital is kind of unto itself and the rest of the school is separate. So it's nice to work at a place like this. So in our group, and I almost used a picture that had you in it, Jonathan, but I figured I better not. So in any case, so the computing infrastructure that we have right now, we have about 12,000 cores. We have 160 terabytes of flash. We have about 11 petabytes of disk. We have archival storage system. We're using GPFS and LSF for the scheduling. We also have a Hadoop cluster. We also have a Hadoop cluster. So for the high performance computing stuff, we have over 1,000 users now. About 200 users are external. And like I said, about 2/3 of the usage is for genomics and about 1/3 is for molecular dynamics simulations. And so we actually started teaching a graduate class in scientific computing to help. I mean, it's maybe what you would think. I think a lot of the folks, I would say, how do I say? I think it's early days for a lot of the biology folks getting into computing, and so I think there's a lot that we can do in terms of teaching and helping people bring them along and use the computing in an efficient and effective way. So we also have a bunch of other parts of the group. People that we have some custom databases for doing clinical trials and things like that. And actually we work with the World Trade Center health program, so that they're tracking I think 48,000, 35,000 first responders. And maybe you've heard about this, the Zagrota Act, I think, that's going through Congress. Actually, it's up for renewal now, but it's just so there's one thing, how do I say, there's one award to track the health and people, they can get health care, but then there's also one, the data center, that looks at, is there a higher incidence of cancer, and and trying to get tease out all that kind of information. So I get to work with those folks. And also, various things related to research computing and other clinical stuff. And also there's the data warehouse. So all the Epic medical records for over 3 million patients get put into this data warehouse every day. And then we have like 25 other databases from clinical and registration and financial and all other things that go in here. And again, it gets used for either the hospital, so they're trying to figure out how to free up hospital beds faster, or things like, we had so many falls last year, why are there so many falls? How does it compare to other people? Or other hospitals? Is it everybody on the night shift who falls? Is it everybody over a certain age who falls? Is it only women who fall? So it's like trying to figure out all that kind of stuff. But then there's also researchers too. So they're trying to, they'll ask for things all the time like, give me all the white males over 50 who are smokers, who are on this drug and this other drug. And they're trying to find different patterns between the data. So so that just gives you some background on some of the things I'm working on, or we're all working on. And so, I was kind of asked to talk about partnering with scientists and what makes, or what do I think is important, or what makes us different than other places, because anyone can set up a cluster and all this. So, I actually spent a bunch of time thinking about this and talking to some other people and trying to tease out what are the main, why is this important? Because users are a pain. I don't know. And so I guess to me, if everybody's on the same page, obviously it's easier to just get things done and to move forward. So, and it helps, not only your institution, but of course it helps yourself too, because it's a small community, right, where people, getting your next job or moving around. There are lots of people who know other people, so it's to me, it's really good to partner and get this. So in any case, when I was thinking about not partnering, I'm like, what are the consequences of not partnering? And of course, I think about Congress, which, and I actually did a search on, partnership in Congress or whatever, and actually this came up for, one-word impressions of Congress, which, I feel like I don't want to be on that list, so anyway. And so, trying to figure out how this all fits into to what you do and the decisions you make. I'm always trying to figure out, when things happen, is this something that, I should speak up about or let go, or, how does it fit into the overall scheme of things? And I think the important thing is to understand how the computing, like what role does that play in the overall business? Because then you can figure out, what's important and what things to fight for and which things that are not going to be, people on, in upper management or whoever are not going to be receptive to. So trying to figure out what motivates these people and how, can you find an alignment of all the interests between what your users want, the management wants, what you want, because otherwise people aren't happy and productive. So I just thought I'd take an example of Mount Sinai about, they're obviously interested in having this translation to, to helping out with medicine. And of course, scientific computing can play a role in all of this, in the education and in the research and in the healthcare delivery. And so that happens to align with my goals, and maybe it was just an excuse to have the bunnies on the slide, I don't know. So I think, to me, to partnering, it's to have a good, to have an approach developed on partnership and trust between you and the scientists that you're working with, right? So how do you do that? I think every place is different, right? So every place has its own institutional culture where they value different things, and I've worked different places that have different, different things that they care about. And, I'll make this, down to things like about the scheduling or about the, so like, some places I worked, they only want to have, they don't care if the machine has a high utilization, right? They just have a lot of big jobs that they want to get through, or even small jobs, but they want the machine sitting there waiting for those jobs to come by, right? And so they get instant access. But then there's also, other places they want to have high utilization because they want to show the machine is super busy so that we can ask to get another computer. So I think it's just trying to understand what the local institution wants and which things are important, so you can help figure out how to move forward and which things to emphasize and which things not to emphasize. So, it's finding out, so like I said, it's finding out what's important and making sure you're all in alignment with your management and with the users too, because what the users want may be totally different than what upper management wants, right? So it's trying to find some balance between all these things. And so one of the things that I think is really important, or that seemed to work well for me, is being transparent, right? So telling people how the machine is being used, creating more awareness of the different issues or the different trade-offs and all these kinds of things. I pulled this page from Nurse because I always like this Nurse page. Is that because you just go to their home page and you get to see what jobs are running now, how many cores are they taking, how is it working. And so you can do, like at Sinai, we have some monitors that are outside our office that show real-time, Nagios display of what's going on, when we send monthly reports to the users, thanks to Jonathan. And all these things just so people understand that they're using it. And even if they don't look at it, or even if they don't look at it carefully, they at least know that we are trying to communicate what's going on. And I think that that's a really important thing to help share this message. So, and of course, customer service, which is important. I mean, I think there was someone else who I was working with when I was talking about this, and he says the way he sees it is, you know, when you go to work with a researcher or a PI or something, you know, in their lab, they're God, but you can't go in there and start telling them how to change things right away. First, you know, you gain their trust, you build some rapport with them, and then you can start telling them how to change things. But you have to at least, you know, start from getting people to work with each other, or getting to understand each other. And the user announcements, I think, is really important. Actually, that was something I learned at SDSC, was, you know, trying to articulate how is this a benefit to the users, right? So we're going to take this outage, we're taking the machine away from them. What are they going to get out of it? And so trying to rephrase, instead of like we're taking a PM to do some obscure thing that no one understands, you know, so that it will be the network will be faster, or so you won't lose data, or I don't know, something that will mean something to the users, so that they can understand why you're taking it away from them. So another thing too is to try to do everything you can to know about the performance and the characteristics of your system before the users find out. So I mean, I remember there was I hate it when users come to me and say, oh, I had this code and it ran this way now, and now it runs this way, and it's a lot slower, and I don't really know why, right? So I think trying to do regression tests, trying to understand, you know, when you first get a system and you take and you understand the characteristics of it, then after you apply upgrades and you do other things, that you're retesting it and you're keeping track of those numbers and comparing them so that you know well about the system, so you understand the status of the system. I mean, other things too, so like there's been users who, I hate getting blindsided in a meeting where someone will say, oh, you know, the system doesn't work and all this, you know, all these problems. And so, and like this is from someone who I thought we had a good relationship and I thought they told me everything that wasn't working. And so I realized some people, you just have to go see them like before the meeting, or once a week or once a month or whatever it is, and just say, hey, you know, what's going on? Because people get busy, they don't want to open up tickets, and you know, at the end of the day, I don't want to go back to I don't want to be accused of the whole list of things from Congress. So it's like some of these things you feel like maybe you shouldn't have to do, but I think they make a difference in terms of how people perceive you and how being able to have a better partnership, right? So if you go visit them and try to find out what's wrong or call them, I found that to be very helpful. I mean, even things like the user surveys and other things are pretty, I found them to be useful. I mean, sure, a lot of people don't fill them out, but a lot of people do, and they'll say stuff. And I think it doesn't have to be complicated. I think you can ask like one question or two questions. You know, what do you like? What do you don't like? What do you wish was? You know, and I think people give good feedback, and I've found that to be helpful. And like I said, the people who don't answer are happy that they were asked. So, and so another things that we've done that has been really helpful is having, you know, different meetings for the different users, right? So like the people who are actually running on the system and who want to understand why the system went down last week, and so to be transparent about what happened and what went wrong, and also try to hear about their concerns. But one thing that has been really helpful is also having like a scientific advisory board where the scientists get together and you kind of help tell them about different trade-offs. So like one that we've had at Sinai is people say, well, you should be backing up all this data and all this stuff. And I say, okay, so you know, here we have $1 million. We could buy a petabyte a disk, or we could buy 2 petabytes. So either we give you 2 petabytes, or we give you 1 petabyte, and we'll make it redundant. And they all voted for the 2 petabytes, right? So they were all complaining, you understand. So it's kind of like not giving people an infinite continuum of choices to make, but giving them some discrete choices. You can have A or B, and you know, and helping them to be partners in making the decision to figure out what to do. And I found that to be effective. So at major points, you know, you have to be careful what you ask for, but if you constrain the choices, you know, it can really help you make decisions that people are happy about. or at least happier about, maybe is a better way to say it. Yeah, I mean, like we allocate the resource. I'm going to talk about that a little bit more in the next slide. But you know, having the annual report, I mean, things like this, or coming up with a strategic plan. I mean, again, these don't have to be super complicated things. They can just be a page. But I mean, again, it's something you can send out to your users and to upper management to explain to them about what are the different things that you have done and that you plan to do. And then people can kind of vote like, oh, this is more, you know, you can say, here's a list of 10 things, but we only have time to do 5. Help us pick which 5 those are. We don't care which they are, but you help pick. And so doing a lot of that stuff I found to be helpful to get people, you know, bought into what you're doing and supportive, right? Because all of you need to have support throughout the organization to survive for the long term. So again, this goes back to really understanding the system and understanding the different components and how they're different. I mean, like with compute time, once it's gone, it's gone. You never get it back, right? Whatever that compute core hour, minute, second, whatever, you already paid for the power and the cooling and everything, or your organization did, and you never get that back. But things like storage, I mean, if the storage is filled up, other people can't run, and then that's, you know, that may be, I mean, it depends on what your overall goals are, whether that's a problem. So you have to figure out how to allocate these different things and share them between different users and figure out how to present them in ways that meet the organizational goals. So, and also I think it's really important to know how well your system is performing and all these things. I mean, I can't tell you how many people I've talked to that I ask them, you know, what the performance is like on something, or how much does it cost to run their system, and they don't know. And I think the thing is that, you know, people, you know, you're always thinking, you know, if you're not doing it effective, you know, in accordance with whatever your organization thinks, then people, they're gonna just take their marbles and go, you know, spend the money at Amazon or go spend it somewhere else, which maybe that is the right thing to do. So I think, but you know, it all depends, right? And it's, you know, it depends on what your goals are, your organization, all this stuff. So, but I think you have to know how you fit into the whole continuum of computing and what value you're providing. And so this one, I don't know how many of you out there know Troy, but he's been at Ohio Supercomputer Center and some other places. But I mean, this is a tough thing, right? Because I think a lot of people get the computing for free, at least in the, you know, and I don't know, let's say the DOE labs and NSF labs and stuff. I mean, you get allocated a certain amount or you get funny money to spend it in certain ways, but it's kind of like, you know, what is it really worth? I mean, people think it's free, so they can ask you to do anything they want. And so how do you show it? You know, if you think something's free, then you don't value it, or a lot of people don't. And so how do you create that value? And I mean, to me, this all kind of ties into understanding what's important to your organization and trying to figure out what the characteristics of your system are and how they're meeting the goals of the overall organization and even the individual goals of the scientists. I mean, most of them just want to get something, you know, get their science done, but they don't, you know, their goals may be different than other goals, but somehow you have to figure out how to communicate that. So, I mean, the allocations is one way, but, and, you know, the human expertise to me is the most important thing of all, actually, because I mean, it's, you know, because people really are different. They really bring different things to the table, and that, you know, they're not just widgets that you take off a shop. There's some people that can accelerate your code way faster than other people, or they'll do it in a different way. I mean, so you have to figure out how to communicate why that's so important, because otherwise then, I mean, everyone should just move all their cycles to Amazon and do something somewhere else. So I don't know if anyone's here from Amazon, but in any case, but it's not a bad thing. I think it just depends on what your goals are and what you're trying to do. So, and so to me, a lot of this, I've been kind of talking about how it's important to know what your organization wants and needs. I mean, I know at Sinai, I'd say they care about the finance, right? So they want to know, like, how do we compare to other places? And, you know, I can tell them this is how much, you know, this is the cost you're avoiding or saving by us running our own operation. But also, and also we've also been able to build we've been able to, because we're there and because we're working closely with the researchers and embedded with them within cubicle farms and other things, we've been able to work on new proposals with them and bring new funding to Sinai, which of course upper management is keen about that, and we're keen about it too because it's new projects that we get to do that are fun and interesting. So also, I mean, they care about reputation and things like this, so talks like this. And you know, we have the service metrics. So I mean, every year I'm always make sure I try to have these numbers at the top of my head so that I can help communicate this to upper management and even to our users so they understand the value that we're providing. And again, this is all for long-term sustainability, right? So I don't want to, you know, I don't want to be hiring folks or working on projects that are only going to be for a year or two. It's like, how do we diversify and make ourselves really valuable to the organization so that we do have a long-term plan and, you know, even when projects come and projects go, that we still continue forward and still have interesting stuff to do. So, you know, trying to make sure, you know, if our overall organization's goals are changing, that we are also changing with them. You know, I feel like, you know, you kind of have to evolve or die, because otherwise then you just, you know, we become a dinosaur and we're not being useful. So you always have to be, kind of have your finger on the pulse of what's going on. You know, and of course the financial piece of it and the intellectual piece. I mean, yeah, so just trying to figure out how to keep things going and keep it interesting. And so as part of all this, we've been, of course, we have to, you know, we've continually looking at what we have and are the machines that we have meeting the needs of our users. And so one of the ways we do that is, I mean, if you ask users what they need or they want, can be wildly different than what's actually happening on the system. And so that's one of the things, we kind of follow this process to try to figure out how the system is being used and then try to pick out some new technologies to help improve it and make it more effective. Because as much as possible, I mean, we'd love to rewrite everybody's code, but it's just not practical, right? And I think that a lot of people, you know, especially in the scientific community, there'll be certain codes that are trusted within the community. So you can't, even if you can rewrite different pieces of it, people won't use it because they'll say, well, that didn't come from this place or that place. It's not the accepted model that's already been verified in the community. So, you know, I'm optimizing for speed or for something else, and they're optimizing for scientific verification, reproducibility, and things like that. So, so to me, what can we do? We can try to optimize. We can try to optimize the machine more to fit the workflow. So, for instance, so this, I'll give you an example of what some of this workflow is like, because it's wildly different than a traditional supercomputing workflow. So a user will submit 10 to 20,000 jobs at one time, and all these jobs run for like 10 minutes at a time. And so and on one core. I mean, this is like, you know, normally I'd say in traditional supercomputing, you know, you'd maybe have one job that's running on 80,000 cores or something at one time and run for days at a time. So this is, as you can see, wildly different. And of course, you know, everyone's just taking whatever the default wall time of a week, right? And even though these jobs are running for 10 minutes, they're saying the wall time for the week. So all the other users are mad because now they think their jobs aren't going to start for 2 weeks or 3 weeks, even though like these jobs are really going to be over soon, and then the scheduler's freaking out. I mean, you can imagine all the things that are going wrong here. And in fact here, and Jonathan may have even done this graph, I don't know. But this is a distribution of the job width and length, so you can kind of get some sense of it. But yeah, 99% of all jobs used only one node, and they took 77% of the core hours. So you can kind of get a sense of what the workload is like. So, and I would say, so that's one challenge, but then also on the I/O was wildly different than I thought too. So there's tons and tons of files nested in, you know, you can see, I think we had, you'll see, so there'll be like 1 million files in a 200 gigabyte directory, and there'll be 10,000 folders. And so some of the folders only have one file in it. I mean, you're like, how could anyone even write software to do stuff like this? But it's real, I can tell you. And people doing inefficient scripting, this ls in a directory of 10,000 files in a for loop. I mean, things like this are typical, I would say. And so, we set up a GPFS file system and, all the performance improvements. I mean, I'm thinking, I knew the files would be small. I didn't think the files would be this small. And in fact, let me show you exactly how small a lot of these files are. But I just didn't anticipate they would be this small. So like all the striping and things that you could get out of GPFS, of course you don't get any of that with this kind of workload. And so I just was 9 million out of 18 million directories only have one file. I mean, 100 million of the files are less than 1 kilobyte. I mean, I don't know. So it's just really stunning to see these kind of statistics. So we were trying to figure out how to do this, and what can we do to help speed the workflow? Because we were getting inconsistent I/O performance, and people are unhappy, and we don't want that, obviously. So we did a bunch of testing. Of course, we did a bunch of testing on testing the different codes on different processors to find out which processors are best suited for this genomic workflow code, but I didn't include any slides on that. But and also we had a lot of trouble with Torque and Moab handling that sheer number of jobs. And so that was a major event, I guess I'll say. So one of the things so this is how we ended up getting Flash actually, was we realized, so we did a bunch of things. I mean, one was, with the new version of GPFS, we could store the tiny files right in the inodes. So we made 4K inodes, and we're storing all these super tiny files right in the inodes, so it never makes it out to disk or anywhere. So that obviously makes it as fast as possible. And then we also have the Flash for the slightly larger files, right? So now people can get consistent performance for all these tiny files. And then we move these files off to slower speed disk. And some of the other people that do have larger files, they never, obviously they just live on that disk itself. So this was something really nice that we've enjoyed from GPFS, and now we can give out consistent file performance and all that, which is really good. And we have a paper at Supercomputing about some of the work we did on this. We also, another thing that we did was we tried to perform some psychology on the users, I guess, which, I mean, over the years, you really can influence user behavior through policies, right? Because the users are always trying to game the system, or they're trying to do certain things. So you can try to encourage certain behaviors. So like, we have a low priority queue that you don't get charged for it, right? So if you don't have anything urgent, then you just run there. And it's surprising how many people are running on that queue. So that frees up more nodes and more things for other people to run who do have higher priority. And we let the users decide if they think their job is high priority or not. They get charged 1.5 their allocations. In other places I've worked, we've charged 2x their allocation to get their jobs, like to have them run next, right? And have them run at a higher priority. We also have a smaller queue that only runs for 2 hours, but then that gets extra high priority, but we only charge them their normal allocation. So again, this is to try to combat some of the wildly inaccurate queue times or wall clock times that people put in their jobs. And so we want to encourage people to get their jobs in the right queue, and we'll turn them around faster, and all this, they can run next, and it frees up more in the machine for other people. Yeah, we've done things, not at Sinai, but giving out allocation discounts to encourage larger jobs to get people to scale up to larger amounts. Kind of scheduling all the full machine jobs. We did this when I was at NICS in Tennessee. We would schedule the full machine jobs only once a week, so we'd back them up, because otherwise the draining from the machine, there's all this. The utilization goes way down, and all these people are unhappy. So we started queuing up all the jobs once a week to do that. So, and so some of the things, because of our partnership with the users, we've been able to bring in some new projects. And so here's an example of one. where we were able to get 5 petabytes of disk and another 2,400 cores from NIH. We got 25 scientists argue that we needed this machine for doing the genomics. So that was really nice. Another project that we just got awarded just last month is this children's exposure, will be the National Center for Children's Exposure Data. So, you know, there's all these studies, they're studying the effects of plastics and lead paint and everything on children. And I guess all the studies are mostly small, and so now will be a data center to collect all this data so people can find patterns in a much larger amount of data. And so this is interesting because there's all these different ontologies and everything that we're starting to learn about is how to track this data and how to see the patterns in it. And so this was an outgrowth of our partnership with the World Trade Center Data Center. So we're looking forward to that. Another, this Clinical and Translational Science Award. So this, we're actually building a de-identified image data warehouse. And so what we're going to be doing is stripping off all of the personal health information from a lot of the images that we have, because there's a lot of people who want to do feature extraction on different images. So you want to see, like, when is the first possible time that maybe that a tumor was appearing. And so people have different you know, visualization algorithms to recognize that. And so we want to have this data made available so people can do those kinds of studies, but also look at, you know, different studies, like everybody who has a certain kind of tumor, what does it look like in different people, so that we can more accurately recognize those tumors. So in any case, so that's another interesting project. And also in terms of education, so like I said, it was kind of helping to build up the knowledge of computing within the bio field. So we actually submitted a proposal to NIH to have 50 grad students come for the next 3 summers. We spent a couple days on scientific computing, a couple days on genomics, and then the whole week on running the genomic pipeline. And so they'll be visiting all different places in New York City for those 2 weeks, and we'll have trivia night and stuff, so that'll be really fun. But this is, you know, to me, it's trying to help bring up the level of computing confidence in the community, and then we won't be having the problems like a billion tiny files. So, I mean, that's what I'm hoping to influence. And we also have, you know, a new master's degree, which we're hoping to attract a bunch of computer scientists to this. Because we need more tools to better do all these things, and people who know how to use the computers and apply it to life sciences. And we have a bunch of things at Supercomputing. Again, we're just trying to engage the community and try to understand better the things that the biologists need, but then also have them better understand the things from the computing side and the things that are possible if the computers are used in a more effective way. And I will lead you with this last slide. We have open positions, so if anyone's looking for a job, come find me or email me, and thank you very much. Thanks.
All right, we have time for a couple questions, if there's any. Yeah?
Oh, no.
What do you think is the difference between computing for healthcare and other scientific institutions versus outside of them?
So you mean, I mean, I guess I would say, I mean, look, to some degree, people are people, right? So, but I mean, so I guess I would say to some degree, people are people, but I would say that I think healthcare, and I feel like at least much of the life sciences, and hopefully I'm not getting into trouble here with anybody, but I think it's early days. So I feel like there's more to be gained, I guess. So, I mean, I think that, yeah, I don't know if that totally answers your question, but I think that, I guess maybe what I would say is, I think maybe I'd say a lot of the healthcare people are more mission driven. Certainly NIH is more mission driven, and it's less kind of, they're more focused on things. So I think in some sense, if you can articulate how whatever you're doing can help get to that goal, that people are really keen to work with you on.
Question here, yeah.
tremendous things happen for anyone. Today I work at Docker. And so my question to you, it's mind-blowing. I'm already working with some universities that the transformation from virtualization to containerization for life science, are you doing anything there? Have you thought about this? I think when you talk about 100 millisecond spin up times as opposed to like 2 minutes.
Yeah.
Times that happen in 400 milliseconds. TTL, anyway, sorry.
Yeah. So yeah, we've been looking at some of those things as part of our evolving, so yes, I think there's definitely a place for that. So, was there one other or Okay.
Yeah. We need to stop for now.
Okay,
for
we
the
can
next
just
few.
stop.
We're a little bit behind schedule, but join me one more time in thanking our speaker.
Thank you.